And when I'll bring it up. Now it should be better, right?
Yes.
Okay.
No,
All
little
right.
bit. Yes. All right.
Okay. Thank you. So thank you for this opportunity to present our work, consensus protocols for improved survivability in autonomous groups of UAV. The work has been done at the National Aviation University, Kiev, Ukraine, in collaboration of several departments. So the context of this work is autonomous groups of aerial vehicles like drones. And the motivation and objectives are to develop dynamical protocols of group flight, examine methods of structural topological analysis of the operational groups of aerial vehicles, and examine possible recovery and remedial actions in case of failures. So just to give a context to this presentation, what we mean here. So there are several modes of operation of aerial vehicles, and most often, even now at present day, what we have is operator-controlled drones. Second situation, which sometimes is seen, is automated system or automated operation of groups of drones. Like in the shows, you can see those wonderful flights of huge number of small drones performing tricks and showing pictures. Those are both are controlled, fully controlled by the ground operator, either after human or automatical. This is not what the context of our presentation here. What we want to focus on is a fully or partially autonomous operation of UAVs in execution of complex mission. So it's not enough for a UAV to be controlled exactly which coordinates and which positions it should take at any moment of time from the ground, as it happens in those shows, because the connection to the operator may not be available for some time, or maybe difficult to maintain for a number of reasons. So here we mean a fully or partially autonomous operation of groups of aerial vehicles in execution of complex intelligent missions. Secondly, we want to consider the mode of control. So there are several approaches to it, and some of them are related to operator control, which is not going to consider here. Two essential ones are related to autonomous operation of UAVs. This is an autonomous controller first, a special element or elements in the group which perform calculations and basically control other members. So it's kind of a hierarchy in the group, management hierarchy. And the second is fully distributed autonomous operations, where each vehicle performs its own calculation and makes its own decisions based on the results of calculations and, importantly, information that it receives from other members of the group. So the question then is, if we can't rely on the central control to tell us at every moment what the direction, what coordinates, what position of a flight should be, how can it be obtained internally by the group? And it appears that there are approaches developed for different systems, which are called consensus protocols, which were implemented here for groups of aerial vehicles. So it's a dynamical system, basically, which is discretized, so made a discrete, and calculation performed at certain moments of time. So here we show how it works and illustrate how it works. And in the paper, of course, it's described in detail. The bottom line is that based on information obtained from other members of a group and certain performed calculations, a vehicle can identify its momentum and its next position in the next moment of time. And this calculation is performed periodically at certain time step, so that every vehicle, based on information that is exchanged, can identify its dynamical characteristics, which are momentums and positions. As numerical simulations performed on this protocol show high level of convergence and consistency. So here on these graphs, we have two groups of model vehicles, a group of 5 on the left and a group of 10 on the right. And what is shown here is the time interval on the horizontal axis and the average error by the element on the vertical axis. And you can see that over time, the error diminishes and the system comes to convergent condition. So the error is minimal. The second aspect we can consider here is topological and structural model. Why we want to consider it, it will be clear very shortly. But basically, one can see a system, a group of aerial vehicles as a graph, undirected graph in some cases, with vehicles as the nodes or vertices and edges as communications channels, connections. And then calculate standard topological characteristics of a graph, which are well known. So why do we want to consider this the structural and topological perspective of aerial vehicles? Well, the answer is quite obvious in the context of the consensus protocols, which we discussed earlier. Because the correctness, the convergence of a protocol depends to a high degree on the availability of information, on the stability of information from all the elements in the group. So if an element or a drone wants to calculate its coordinates in the next moment of time, it needs the input from all the elements in the group. And if for some reason the information is not available, then instead of converging, the system may go into an unstable mode. So the calculations may be inconsistent between different elements, and it may not be able to maintain a stable formation. And here is an example of such situation. This is a model example. On the top left, we can see that suppose we have this formation of aerial vehicles, of 5 vehicles here. And these are communications channels. For a number of reasons, we can consider, we can assume that the elements can talk only along the edges of a graph. So the problem becomes apparent instantly when we have analyzed the topological characteristics of such group. We can see that it's inhomogeneous. So one of the elements, the central element here, is important for communications between many elements of a group. So if something happens to this element, the connections between elements can be lost, and that would be a problem for the convergence protocol, because it wouldn't be able to operate in the convergence mode anymore, as the information exchange is terminated between certain elements. We want to be able to identify these vulnerabilities, these scenarios where due to certain layout or certain management decision of a group, the vulnerability and the risk of failure increases. And that's exactly what topological structural analysis allows us to do. By calculating standard well-known characteristics of topological systems, we can identify the elements of formation which carry higher risk of failure. And then, of course, based on this input, take some decision to mitigate this possibility of failure. One of these examples is shown in this slide here. By a simple decision in the example considered before, with a simple change of formation from flat to 3-dimensional, we can make this core element, central element of a group, just a regular element, and the whole group becomes homogeneous. So the failure of an element wouldn't affect the operation of the whole group. Conclusions. So convergent autonomous operation of aerial vehicles is possible and feasible based on the proposed dynamical convergence protocols. Structural and topological analysis is important and essential for reliable operation of autonomous groups. It can help identify vulnerabilities and design preventative measures to improve robustness and resilience of a group. Can assure stability and resilience of autonomous groups in execution of complex intelligent missions. So this direction of research answers some practical and essential challenges in development of autonomous intelligent groups of aerial vehicles. Some references here. Much work has been going on in this area. Publications in the now and associated partners. And thank you for your attention.
Thank you very much, Sergey. I'm sorry, I made a mistake at the beginning. You look like another professor from Napoli University. but I have one small question. Do you plan to test your approach or your protocol on any UAV platform? If yes, can you name an example of such a platform?
All right, this is a good question. This approach is being developed, so we are going layer by layer. So this article was related to group flight. The next important part, of course, is communications and navigation. No system can operate without reliable solutions for communications in the group, in the autonomous group. And navigation, ability to follow the prescribed mission. So this work continues, but we do hope to develop working prototype at some point. So demonstrate these concepts not only in theory but in practice.
Thank you very much. Have you any questions, dear colleagues, to Sergey?
I have a small question.
Okay, Alex, please.
Okay. Say, how the biggest distance can be between separate drones in group of drones in your approach?
All right. So this was one of the criteria. The dynamic protocol, one of the dimensions of a dynamic protocol is to ensure that the minimal distance between groups is, first of all, detected and then maintained. So there are details of this are in the paper. So it's a dynamical question of solution of dynamical equation to say it shortly.
And I may add, according to target task, distance between drones and opportunity of each drones in group. According to
it's one of the conditions of a dynamic system of equations, or a discrete system of equations, which is basically an input to the calculation.
Okay, thank you, Raj.
Thank you, dear colleagues. Have you any questions to Sergey?
And I have one question. Dear Serge, what are the limitations of your approach?
Limitations are more on the size of practicality. So there, the task is simple, and there the number of elements in a group is small, and that's one of the limitations. And where operator control can be maintained, there is no problem with the operator control. When it's just there is no point in going to this complexity, and the standard existing methods can work well. But in a specific applications where the system cannot rely on the ground control at all time for the whole period of operation, where the mission is sufficiently complex, so the group has to make their own decisions and cannot rely on the ground control. In this area of applications, our approach may be the most promising at this time, as far as we know.
Thank you.
Thank you. Any question, please? No question. Sergey, thank you very much for your research and for you and for your colleagues. And next.